Imagine a nuclear reactor that's efficient, clean, and safe from meltdowns. Sounds too good to be true. It's the promise of molten salt reactors. Unlike traditional reactors, which use solid fuel rods and water as a coolant, these reactors uses liquid fuel dissolved in molten salt. This unique design could make nuclear energy safer, cleaner, and more sustainable. Molten salt reactors were first explored in the 1950s and 60s, but interest faded as traditional uranium reactors took center stage. Now, as the demand for clean, carbon-free energy grows, scientists and engineers are giving MSRs a second look. These reactors have incredible potential to address many of the concerns people have about nuclear energy, from waste and safety to fuel efficiency. But what makes molten salt reactors so different, and how exactly do they work? Are they truly the future of nuclear power, or is there more to the story? In this video, we'll dive into the science behind MSRs, explore their unique benefits, and examine the challenges that must be overcome to make this next-generation technology a reality. Molten salt reactors, or MSRs, operate quite differently from traditional nuclear reactors. In a conventional reactor, fuel is in solid form, usually uranium pellets packed into rods, while water serves as both the coolant and the source of steam that drives turbines. But in a molten salt reactor, the nuclear fuel is dissolved in a mixture of molten salt, which acts as both fuel and coolant. This liquid state changes everything about how the reactor operates. In an MSR, the fuel-salt mixture flows through the reactor's core, where nuclear fission reactions occur. As the salt heats up, it transfers thermal energy to a heat exchanger, which in turn heats up a secondary loop. This secondary loop then generates steam to drive turbines and produce electricity. Unlike traditional reactors, which operate under high pressure, MSRs run at low pressure, which reduces the risk of a catastrophic explosion. One of the fascinating features of molten salt reactors is that they can be designed to use various fuels. While some MSRs use uranium, others are designed to use thorium, a more abundant, potentially safer alternative. Thorium MSRs have the added advantage of producing less long-lived radioactive waste. Because molten salt reactors operate at high temperatures, they're highly efficient at converting nuclear energy into electricity. This efficiency, combined with the liquid nature of the fuel, allows for more flexible and stable reactor operation. Additionally, if the reactor overheats, the molten salt will naturally drain into a safety chamber below the reactor, stopping the reaction and avoiding a meltdown scenario. With their ability to use different fuel types, operate at high temperatures, and incorporate passive safety features, molten salt reactors represent a major shift in nuclear reactor design. By understanding the science behind MSRs, we can appreciate why they're gaining attention as a next-generation nuclear technology. Molten salt reactors have several advantages that make them promising for the future of clean energy. One of the most important benefits is safety. Unlike traditional reactors, MSRs operate at low pressure, which greatly reduces the risk of an explosion. Because the fuel is dissolved in molten salt, there's no need for high-pressure water to cool it, making the reactor inherently safer. Another key safety feature is the passive cooling system. In a conventional reactor, if the cooling system fails, there's a risk of overheating, which can lead to a meltdown. In an MSR, however, if the reactor overheats, the molten salt will naturally drain into a safety chamber below, where it cools down and stops the fission reaction. This passive safety feature means that even in an emergency, the reactor can safely shut down on its own, eliminating the need for complex emergency protocols. Fuel flexibility is another major advantage. Traditional reactors primarily use uranium, but MSRs can use a variety of fuels, including uranium, thorium, and even spent nuclear waste from other reactors. Thorium is an especially appealing option because it's more abundant than uranium and produces less long-lived radioactive waste. This flexibility in fuel types could make MSRs a sustainable option for countries that lack large uranium reserves or want to minimize nuclear waste. MSRs are also highly efficient. Because molten salt reactors operate at high temperatures, they're able to convert nuclear energy into electricity more effectively than traditional reactors. Higher temperatures allow the reactors to reach greater thermal efficiencies, producing more power with less fuel. This efficiency not only reduces costs but also makes molten salt reactors well-suited for industrial applications, such as generating heat for chemical processes or hydrogen production. Another significant advantage is waste reduction. Traditional nuclear reactors produce a considerable amount of long-lived radioactive waste, which requires careful handling and long-term storage. In contrast, molten salt reactors produce waste that is much less hazardous in the long run. Some MSR designs can even recycle waste as fuel, reducing the need for disposal. This makes MSRs an attractive option for sustainable nuclear energy, addressing one of the major concerns associated with traditional reactors. Finally, molten salt reactors have the potential to be more environmentally friendly. With their ability to use alternative fuels like thorium and recycle existing waste, they offer a cleaner alternative to fossil fuels and even to traditional nuclear energy. By producing less long-lived radioactive waste and eliminating the need for large cooling towers or high-pressure water systems, MSRs present a more sustainable nuclear option for the future. With these safety, efficiency, and environmental benefits, it's easy to see why molten salt reactors are generating interest as a next-generation nuclear technology. But as promising as they are, there are still challenges to overcome before they can be widely adopted. One of the primary technical hurdles is corrosion. Molten salt is highly corrosive, which can cause significant wear and tear on the reactor materials. To handle this issue, engineers are developing advanced materials that can withstand the harsh conditions inside an MSR. However, finding materials that are both durable and cost-effective remains a challenge. Because molten salt reactors operate at extremely high temperatures, reactor components must endure prolonged exposure to intense heat without degrading. High-temperature alloys and ceramics are being explored as potential solutions, but these materials are often expensive and difficult to manufacture in large quantities. Until more durable, cost-effective materials are available, the widespread adoption of MSRs will be limited. Another challenge facing molten salt reactors is regulation and licensing. Traditional nuclear reactors have been around for decades, and regulatory frameworks are well established. However, MSRs operate on a completely different principle, with liquid fuel and lower pressure. This means that current regulations don't always apply to MSRs, and new safety standards and licensing processes are needed. Developing these regulatory frameworks is a complex, time-consuming process, requiring close collaboration between engineers, scientists, and regulatory bodies. Building a molten salt reactor is a complex and expensive undertaking, and while the technology is promising, it hasn't been proven at a commercial scale. Governments and private investors may be hesitant to fund large-scale projects until MSRs demonstrate their viability. To overcome this, some countries are investing in prototype reactors, while private companies are working to bring down costs through innovation and scale. Despite these challenges, molten salt reactors are gaining momentum in research and development. Countries like China and the United States are investing heavily in MSR research, with China expected to have a fully operational prototype soon. Private companies, such as TerraPower and Thorium, are also developing advanced MSR designs, each with unique approaches to solve these engineering and regulatory challenges. The potential applications of MSRs are also expanding beyond electricity generation. With their ability to operate at high temperatures, these reactors could be used for industrial heat applications and hydrogen production. This versatility makes molten salt reactors appealing for industries that require high temperatures, such as chemical manufacturing and steel production, as well as for future energy systems that rely on clean hydrogen. As research and development progress, molten salt reactors may overcome these obstacles and become a viable, safe, and efficient source of energy. But achieving this vision will require continued collaboration across industries, governments, and scientific communities. Molten salt reactors represent a bold step forward in the world of nuclear energy. By addressing long-standing concerns about safety, waste, and fuel efficiency, these reactors could offer a cleaner, safer, and more sustainable form of energy. With the flexibility to use various fuel types, including thorium and recycled waste, MSRs have the potential to reduce our reliance on fossil fuels and minimize the environmental impact of power generation. But while molten salt reactors offer incredible promise, there are still significant challenges to overcome. From material durability and corrosion to regulatory and economic hurdles, a lot of work remains before MSRs can reach their full potential. With ongoing research, international collaboration, and investments in prototype development, molten salt reactors could become a viable energy source in the coming decades. If you're excited about the future of clean energy and the possibilities of advanced nuclear technology, make sure to subscribe to our channel. Give this video a thumbs up and share it with anyone who's curious about new energy solutions. Together, let's explore the technologies that could transform our world and lead us to a sustainable future.